computer. Go. All right, the next speaker is David Magness. We're going to talk about kinetic Monte Carlo simulations of atomic layer deposition.
Thank you very much. You stole my opener. My name is David Magness, and again, I'm going to talk about kinetic Monte Carlo simulations and how we can use these to simulate atomic layer deposition. This project was done under the advisement of Dr. Sakija. So just to outline, I'll talk about the ALD process. There will be two actually that I'll discuss, and then I have a short animation about those. I'll talk about the KMC method and how we implemented that to model these processes. I'll go over my results for zinc oxide deposition. I'll update you on our progress simulating alumina deposition. I'll lay out a few paths forward for this project, and then at the end I'll kind of thank some important people, cite some sources, and be happy to take your questions. So the ALD process is a type of chemical vapor deposition, or CVD. This is where we admit gaseous precursors into a chamber. This is called a pulse. We'll do this in an alternating sequence. There's more than one type of precursor used, typically. And in between each pulse, we will purge the chamber using a pressurized inert gas, typically argon. Here are some important players. On the left-hand side of the screen here, you can see diethyl zinc, or DEZ. I'm going to throw a lot of acronyms at you, so just bear with me. This is a zinc atom that is sandwiched between two ethyl ligands. And this is the metal precursor for zinc oxide deposition. On the right here, we have trimethyl aluminum, or TMA, an aluminum atom that's centered between three methyl ligands. This is the metal precursor for alumina deposition. In the center, we have a water molecule, and this is the second type of precursor for both deposition processes. Here we'll use zinc oxide as an example. So at the top here, zinc in blue, oxygen in red. We have one layer. This is hexagonally packed zinc oxide in the 0001 direction. On top of it, we have a layer of water molecules. What happens during the first DEZ pulse is that the DEZ will donate, the DEZ will rob hydrogen from one of these water molecules. This ethyl ligand will then form ethane gas and then be released as a byproduct into the chamber. This byproduct doesn't interact with the surface, and so in our simulations we can basically just neglect it. There is no ethane. What's left on the surface is most important. We have MEZ, or monoethyl zinc. It's just a zinc with one ethyl ligand attached. And this reaction occurs pretty quickly. When we look at our simulations, we don't really see any DEZ. It actually gets converted to MEZ almost immediately. I know this because we had to turn down our simulation steps to about 10 to the negative 6 seconds in order to see any DEZ. For the remainder of the pulse, these oxygen atoms will basically trade hydrogens back and forth in a process called proton diffusion. So basically, after MEZ is formed, these atoms basically play a molecular hot potato until the next pulse. We'll purge, and then we have an H2O pulse. Again, the water donates a hydrogen to the ethyl ligands that are on the surface. And this cleanses the ethyl ligands, forming ethane again as a byproduct. Now you should notice that there is still MEZ left in the surface. Most likely what will happen is that these ligands will get trapped in the surface as the material is formed. The next slide is a 20-second animation of this process happening. So the pulse and purge are indicated by blue and red. So that's going to be the pulse. The purges are represented by white. So you kind of see what I mean. So they're just playing that molecular hot potato back and forth. H2O purge cleans most of the ligands. And you'll see it slowly will cleanse some of the ligands. Unlike the DEZ pulse, the H2O pulse takes a longer time in order to do its job. This process will just repeat. And so we'll get something similar to this. On the left is the substance after 8 layers of deposition. On the right, we have the substance after 16 layers, or 16 deposition cycles. And in fact, this material would keep on growing had I let the simulation run for a longer time. So the images you just saw were from an on-lattice KMC. This means that, like a 3-dimensional chessboard, we have a lattice, 3D grid, where pieces can be. Okay, and we have different pieces at each of these sites. The green here represents vacancies, so there's actually nothing there. So we can just ignore them. And you'll notice that we have the blue and red zinc and oxygen sites here at the bottom, just like we did in our initial simulation start. The cream-colored sites here represent the oxygen, the water molecules, I'm sorry, here. So you can see this is just a painting. As far as our simulation is concerned, we only have a bunch of sites, and each of these sites has a different site species. Okay, so we could have an oxygen, a pure zinc, we could have a water molecule, we could have a DEZ molecule, or any combination thereof at each of these sites. We adopted this KMC code from Drs. Matti Shirazi, Simon Elliott, and Timo Weckman. These are researchers in Finland. Dr. Shirazi and Elliott put together the first 3-dimensional KMC code for hafnium oxide. Dr. Weckman came behind those two gentlemen and revamped the code so it could handle zinc oxide. What we've done is replicate Dr. Weckman's work with zinc oxide, mainly to calibrate myself to make sure that we're using the code correctly and we have a proper understanding. We've expanded on that a little bit and used it as a springboard to simulate alumina deposition. KMC works by generating 2 random numbers, row 1 and row 2. Row 1 selects an event, J, from an event list. And so basically this row 1 helps it pick an event that has a rate coefficient K that is just higher than it. The rate coefficient here basically represents the frequency of how often that reaction should occur. The second random number, row 2, advances the time step. So we take the natural log of row 2, divide it by the sum of all the rate coefficients in our event list. Now this is kind of an important thing to note here, because if our event list boils down to nothing, then the sum of our rate coefficients is 0. We can't divide by 0. So what happens is the simulation will jump to the end, and it's basically a useless simulation. So it's important to have a full reaction list. That way things can keep churning as the simulation progresses. Here's an example reaction list. It's just an excerpt, actually, from zinc oxide. The first three reactions here are the adsorption of DEZ. And you can see here we have site 1, if it's a water molecule. This should be a 2 here. DEZ and water is what it becomes. So you have a water molecule, and then at that water molecule, if the DEZ attaches to it, that site now becomes water with a DEZ on top of it. That DEZ has a chance of desorbing, so it's just the reverse of the first three reactions. Additionally, we have our first ligand removal in these next two. So you can see we have DEZ, represented here by ZnX2 on an oxygen. It will rob a hydrogen from its neighbor. So its neighbor will turn from OH to pure oxygen, and the original site will go from DEZ on an oxygen to MEZ on an oxygen. Final reaction I'll discuss today is OH to O, and its neighbor goes from O to OH. This is how the simulation counts proton diffusion. So you can see it's just trading that hydrogen back and forth between the two sites. Each reaction has a rate coefficient K. All the adsorption reactions have a certain rate coefficient. All the surface reactions that happen have their own rate coefficient. The water adsorption has its own rate coefficient, so there's 3 rate coefficients that we need that cover zinc oxide. The energy barrier here, where it's 0, it's basically negative. Our code can't handle that, so we just call them 0. But down here for proton diffusion, for example, we have an energy barrier of 0.4 eV. And I'll discuss how energy barriers are important later. So the rate coefficient, again, for the adsorption reactions are governed by this equation from kinetic gas theory. And then for surface reactions, this is the equation that we use. So adsorption reactions are dependent on pressure and temperature. Surface reactions are only dependent upon temperature here. To get the energy barriers, we use a Python library called GPaw. And this will perform DFT calculations, density functional theory. This is where the quantum mechanics comes into play. The algorithm works as follows. We will take an initial guess for the electron density. The program will use that to calculate an effective potential. We'll use that to solve a set of Kohn-Sham equations. That'll give us the electron density. If that density is in agreement with what we started with, then this is self-consistent, and we can get our energy and the optimized geometry. And this is important because our system conserves energy. There are a couple of pros and cons with this method of simulation. Most simulation software will, if it's classical, repeatedly solve Newton's equations. If it's quantum, it'll solve the Schrodinger equation, for example. These methods can only handle between a couple of atoms to hundreds of atoms at most. In our KMC software, we are actually dealing with tens of thousands of atoms, so that's pretty cool. Additionally, KMC is called multi-scale modeling because we can combine quantum mechanics and classical mechanics using the energy barriers and the rate coefficients. So this allows us to cover huge time steps, whereas classical simulations can have time steps of picoseconds, if we're lucky. Here we're talking about milliseconds in our time steps. So that allows us to run simulations covering about 20 seconds of deposition or greater. This would be impossible with classical molecular simulation packages. There are a couple of cons to this. First off, we need a complete reaction list. So the process that we're studying or simulating has to be well known. A lot of the heavy lifting has to be done in advance. So to get these DFT calculations, it can take sometimes days. And we have to do that for each event in our event list. Additionally, because there is a stochastic nature behind KMC, it's a random type of code, we have to average together several simulations in order to get a general idea of what is happening. So here is some data that we've gotten from the zinc oxide code. You can see this is mass in nanograms per centimeter squared, and then time on the x-axis. This curve has two forks, two branches. The upper branch is deposition at 400 Kelvin. The lower branch is deposition at 300 Kelvin. I ran several different pressures for each of these temperatures, and we can note that for the higher temperature, pressure really didn't matter. For the lower temperature, pressure did matter. We saw more of a range in answers and ultimate mass when we use a lower temperature. You can see that during the blue, this is during the pulse, and this is where we get the highest mass gain, is during the DEZ pulse. During the H2O pulse, we really don't gain any mass. This is because we're releasing ethane and only gaining an oxygen and a hydrogen. This is another graph of zinc oxide, the same simulation. Here we're graphing site species. So in blue and red, we have zinc and oxygen, respectively. We can see that they jump up during the respective pulses, as we would expect. The most interesting fact of this graph here is right here. The gray represents the amount of hydrogen in our system. And we have a slightly lower amount of hydrogen in the high temperature run compared to the lower temperature run. This basically means higher temperatures give us a slightly more pure substance. There are a couple of differences between zinc oxide deposition and alumina deposition. Specifically, the alumina deposition has a TMA, trimethyl aluminum. It has 3 ligands rather than standard 2 with DEZ. There's another little caveat in here as well. Monomethyl aluminum, when we boil down to aluminum with 1 methyl ligand, it cannot be attacked by a single water molecule. Dr. Weckman found in his DFT calculations that we first had to attack the MMA with a single water molecule. This opens it up to attack from the opposite side from another water molecule. This is what removes the MMA ligand. And we're just left with, again, a hydroxylated surface here. This is a mass graph for the alumina deposition. Again, I talked about how we had to have a complete reaction list, otherwise the simulation would jump to the end. Here, we don't see any growth or as sharp an increase in growth during the TMA pulse, because I have artificially reduced the rate coefficient for TMA adsorption. So these sharp steps here are actually increase in mass during the water pulse. I did this again because the simulation was jumping to the end. So if I slowed down those reactions, it kept things puttering along until another event could occur. So paths forward. We'd like to finish our analysis on alumina simulation and simulate some more with that. Additionally, there's some interest with variable field assisted atomic layer deposition. So this is where we turn on an electric field during our deposition process. And this can orient, for example, water is a polar molecule, so it can orient in a different fashion. And we could potentially get different energy barriers for these reactions. We can also modify this code for other atomic layer deposition processes. It's not limited to just these, but more work needs to be done to get this code to where it can handle that. So here are my sources, and I'd like to thank Dr. Weckman and Dr. Shirazi, Dr. Sakija, and our very own Bikash for his expert technical help getting this code to run on our cluster here in Canberra. Are there any questions?
Thank you, speaker. Any questions for David? The room is silent. What about Zoom? Just gotta ask the first question.
Come on, softball question.
So, David, I have one question, maybe,
Yes, sir.
So, what is the typical thickness, right? Say zinc oxide or aluminum oxide, right? So, what is the typical thickness one can grow through ALD?
So that's a good question. I don't have the numbers in terms of like angstroms or nanometers, but we have been able to simulate simulate growth for as long as we want to actually run the simulation. So at least 16 to 25 layers of zinc oxide.
Okay. So then, yeah, okay, one more question is, you say Kinetic Monte Carlo, right?
Yes,
simulations, what you're doing here, right?
Mm-hmm.
So then this is the software available, or you develop using MATLAB or some?
So that's an excellent question. This code takes advantage of a Kinetic Monte Carlo package called Sparks. Mm-hmm. It's written in C++, and Dr. Shirazi and Dr. Weckman put this together using the Sparks package.
Is it a free software, or you need to buy or?
Sparks itself is free, and the code has been published on GitHub. However, we actually spent about 8 months trying to find out where there was an error in this code. So there actually isn't a working code that has been published yet.
The Sparks that David was indicating, it's all from Sandia National Lab actually. So the original code is the same as where LAMB was originally, and then the Timo and Weckman and Shirazi modify that so that will be work for ALD. So they further developed it for ALD. But technically, it's a general purpose KMC that is made available by Sandia National Lab.
Okay, so Ridwan, the question here, so can you do magnetic, hysteresis, right? Phase transitions, all kind of things,
so
right?
so if it's a general purpose KMC, and so I think in principle it should work so long as, of course, it has to be it's general purpose for random, basically random numbers code. The only thing is just you have to create what is the purpose. So one example that people use is actually for nuclear application or wave formation, that kind of thing, basically. So I'm sure, I don't remember, David, do you remember of any other examples this KMC is being used for?
Icing models, yeah, I know there are a few of those.
Grain growth, right? I think that's another
yes,
also.
yes,
like a POTS model. Yeah. So if you can do top POTS model, I assume magnetic basically you can do the same thing. Yeah.
So can you do Ising model, Heisenberg model?
I think, because it's a grain growth sort of equivalency of domains in that sense, yeah.
Oh, okay.
Yeah.
Can I ask a question? Since you talk about grain growth, can you model defects?
So,
usually when there's growth, there's
right. So we're using, because of the on-lattice nature, there's going to be some defects in the form of encased methyl ligands or ethyl ligands. But because, again, it's kind of an ideal lattice around it, it kind of just grows around those ethyl ligands and doesn't interact with them. So there are defects, but not in the lattice itself, just in what is at the certain sites in the lattice. Yeah.
That's an excellent question, Big, because that is basically ultimately what you want to know. Is whether or not we can do defects.
Part, right? Magnetic part, right? Whether we can do something like that too, right?
Yeah, and I'm not sure how we would incorporate magnetic effects. Like I said, I know that we can incorporate the electric field by changing our DFT calculations. So to be honest with you, I'm not sure how we would go about that.
No, people do magnetic properties, right? Using Monte Carlo, right? So then surely.
Yeah, Dr. Ghosh, the magnetic properties, there is an algorithm, it's Metropolis algorithm. It also uses Monte Carlo algorithm. So yeah, it can be, the properties can be done from that.
Okay.
So I just did a very simple, very basic simulation in the last semester, but I don't know the implications. I'm not quite sure what can be done with that algorithm for this kind of projects.
Yeah, no, I recently heard somebody gave a talk on Purcell nanoparticles and Monte Carlo stuff. So that's what I was thinking, how you can predict or, image loop or then phase transition, those kind of things, right?
David, I have a question.
Yes,
This is
sir.
Dr. Mijanovic. So the kinetic rate constants that you use, are those actually fashioned after experimental values, or are they just chosen so as to make your MC calculation work?
So we didn't choose them the only choosing that I did was in the Illumina code. The rate coefficients for the zinc oxide was from Weckman's calculations based on those equations that I showed. The rate coefficients for the Illumina code mainly came from, again, Weckman's calculations. The only difference there was the rate coefficient for TMA adsorption. That was the one that I artificially depressed in order to keep everything going. So I don't know that they were necessarily experimentally determined, but theoretically determined from those equations that you see here.
all right. If there are no other questions, let's thank David and Tahir again. And I think this worked well, having seminar via Zoom and people sitting in their offices. So next week we'll have an external speaker. So that means we won't be here. I will be at my desk and get the whole process going via my computer there. And then you guys sit whatever you want. Okay. Thank you so much.